Robert. So what's the difference between LLM inference and regular inference?
Well, there's so many important differences between LLM inference and regular inference.
Battery,
yeah, I mean, there's a reason you have specialized inference engines like vLLM, SGLang, TensorRT-LLM, and so forth. To start off with, large language models do variable length computation, right? You have variable length inputs, you have variable length outputs. That's very different from, say, a traditional convolutional neural network that you might use for computer vision, where you have a fixed size image input and are doing a fixed amount of computation and then generating some label as your output, right? What's hard about variable length computation? Well, one of the most important techniques for getting good performance out of inference is batching, right? You don't want to just process one item or one data point at a time. You want to process a batch of items at a time because the overhead is not linear. It's not that much more expensive to process two inputs than it is to process one input. So you want to do a bunch of them at a time to get good performance. But if you are batching your requests together and each one requires a different amount of computation, some are going to finish earlier, some are going to finish later. You have to continuously swap in new queries to process and sort of continue to fill up the batch. And so that leads to a specific technique called continuous batching, which is important for LLM inference but doesn't come up with regular models. So that's the first thing, is continuous batching and variable length computation.
Yeah.
Another technique that comes up a lot with optimizing performance is that LLMs have these two different stages of computation for doing inference. You have the prefill stage, which is about processing the input query, and then you have the decode stage, which is about generating the output response one token at a time. They have very different properties. The prefill stage is often compute bound. The decode stage is often GPU memory bandwidth bound. And the techniques you might use for scheduling and the resource requirements for these different stages can vary quite a bit. And if you schedule them on the same GPUs, they can interrupt each other, lead to less predictable behavior. And so what's a common technique for getting good performance is what's called prefill decode disaggregation. Disaggregation meaning you separate them out and you run them on different pools of compute. So you run the prefill in one set of pool of compute, decode in another place, move the data in between. That can lead to much better performance or much more predictable performance. So that's the second thing I would say. Different stages of compute with different characteristics that need to be separated out.
Yeah. What's the third?
Third, so GPU memory management is a way harder problem with LLMs than it is with regular models. With regular models, it's far more predictable. Here with LLMs...
We don't want to get run over. Hold on, we're crossing the street.
So here with
LLMs.
Yeah, with LLMs, first of all, there's a ton of caching that's very important. Imagine you are doing a multi-turn conversation, and you can think of that as each turn in the conversation is a different query to the LLM.
Each turn.
Yeah, it's different. A different query to the LLM, but with a shared prefix. And when you're sharing the prefix, that means there's a lot of redundant computation that's overlapped between the different queries. And so you want to reuse a lot of that computation, a lot of the intermediate activations that are computed. And this is what's called the 𝗂 cache, or the 𝗂 vectors that are computed, and you want to reuse those, right? There's all sorts of questions around which ones to reuse or to cache, which ones to recompute, right, in order to save memory, how to manage that memory, when to swap it out somewhere else, right? One of the big innovations of vLLM was this technique called page detention, which draws inspiration from virtual memory to more effectively manage GPU memory, manage the 𝗂 cache, and avoid fragmentation. So GPU memory management is far more complex with LLMs, so that's number 3.
So what's the fourth one?
So this thing just buzzed.
No!
We can...
Don't die on me! There's a fourth one that we didn't get to because our mic died. 10% battery, we got through 3 of them. Now we do not have a mic, but we are continuing because we're here to finish explaining to you the difference between LLM inference and regular inference.
Yeah.
So fourth reason.
Yeah, so the fourth thing I was going to say has to do with routing. And when you're scaling regular model serving, you are typically replicating the model, and then as new queries come in, you route them to a different replica, perhaps in a round-robin fashion. Perhaps you choose a couple random replicas and then route to the one that is less busy, right? All of these work very well. Now, with LLMs, because there can be so much shared computation between multiple different queries, because you're doing all this caching, you typically want to route the query to a replica that has the relevant stuff cached. Essentially prefix-aware routing. So just fundamentally you end up with different routing strategies.
Listen, we did pretty good for 10% charge.
Yeah.
We lost the mic.
One more I want to talk about.
Okay, we have the camera still going.
So the fifth thing I would say is model sharding strategies can be quite different for LLMs. Again, when you're scaling model serving for regular models, you are often simply replicating the model across multiple GPUs.
Yeah.
Now, one interesting thing that comes up, which you have with LLMs, is you have large mixture of expert models. So these models interweave attention layers with layers that have large numbers of experts. And experts you can think of as essentially many different sets of weights that can get activated differently, depending on the query in a dynamic fashion. What's common here is there are many different strategies, but one example is to replicate the layers across all of the GPUs and then shard the expert layers across the different GPUs. And then as a query is being processed, it will sort of be routed dynamically to the appropriate GPU based on which experts are being activated. And that's a fairly sort of complex setup. So it's not like there's the 10 different distinct model replicas. It's in fact just one big replica with a bunch of crazy routing inside of it. And so that's something that really only comes up with large mixture of expert models.
Yeah, so how common is that use case?
Oh, it's becoming super common. I mean, a lot of the best models are these large mixture of expert models. But just to reiterate, this is why you have specialized inference engines for LLM inference. So things like vLLM, SGLang, and so forth. And of course, Ray integrates with all of these to make it easy to set up prefill decode disaggregation to provide that layer of prefix-aware routing to set up the large mixture of expert models to be able to optimize performance and scale all of that.
Vlog style.